more complex. And the point is, in fundamental domains, you have to worry about boundaries because going from here to here, this is related by an element of the group, and so you want to include this boundary but not that boundary. So basically, this stuff in the solid blue is included, the dotted stuff is not. So that's the fundamental domain of this particular congruent subgroup. So what I do is I pick. So if I'm going to solve this equation. Remember, I want to solve this equation. So first, I can pick a solution that's in the fundamental domain. So I can call that tau naught. And so tau naught does that. And then the point is, all the other solutions, again, because of this isomorphism, all the other ones, basically they're all related by the group action. And so basically, once I have tau naught, I just act on it by the group, by the fractional linear transformations, and I get all possible taus. So what we get is all possible taus. We now understand what they are. We find one in this fundamental domain. We hit it by these linear fractional transformations, satisfying these properties, and you basically get everything you want. And then the other thing that's the miracle is the fact that I'm in the fundamental domain means that this guy is the simplest value. So remember that's the one we always make the right choice when you do the AGM sequence. And so that's the thing, is that notion of the simplest choice, that's basically saying that I'm picking the one of the taus that happens to lie in the fundamental domain. So it's that combination of things coming together that gives some of this theory its real power. So that's really nice. So we now understand precisely what's going on for solving this equation. Now, what I have to do is, remember this was the simplest value, but now I have to take this p and apply it not just to this one, but these guys. So what is p going to do to these guys? So that means I have to understand what kind of function p is. And the point is that p of tau squared is a modular form of weight 1. And remember, modular form means that it's not invariant. It's sort of when you hit it by a group element, you get sort of a fudge factor. It's basically a power of c plus d tau to the weight. And here the congruent subgroup is this one. I call it gamma. It's a 2 with a little 0 there because it's just a slightly funky group. And so it's basically, again, mod 4. You want the diagonal elements to be 1 mod 4. And then the off-diagonal elements, you want them to be even. So that's basically what you want here. And now let me sketch a proof of the main theorem. And so basically, the values are going to be mu. So remember how we get a value of the AGM. We take our b over a, we solve this equation, we find a tau, we plug the tau into here, and compute mu prime that way. And so that's the game we play. And so then what happens, so what's 1 over mu prime? Remember, our formula had 1 over mu prime, so we take 1 over mu prime, so it's just the reciprocal of that. But notice that's now p of tau. But remember that tau is one of our elements of this group applied to tau naught, and that's what gives the simplest value. And now we use the fact that this is a modular form. And so basically I get just what it does to p of tau naught, but I also get the c tau plus d to a power, but because it's weight 1, that's just the first power. And the reason this works is because there are different groups involved, but this group, and that's the one that relates the taus for k prime, that group is a subgroup of the group that works for p of tau squared, and so this actually still works. And now you just multiply this out a little bit. So let me take the d, I'll take d times that, and I get d times p of tau squared over a, so I get that guy. And then I also get this one, which is this one. But notice that right here, that's the simplest value. And so and again, that's because that lies in the fundamental domain. So here we have, and so in fact, notice that here we have d over mu, where that mu really is the simplest value. And then here you have to do some work that you have to show what this guy is. And so it turns out that what happens here is that when you play the game, what you discover is that this guy right here up to value of I is basically the simplest value of na plus b and a minus b. So this is some details that I'm certainly omitting. But the point is, it really is the fact that I have modular functions, k prime, modular forms of weight 1, p squared. That's the heart of the proof, is understanding how these things together. So that's basically a sketch of the proof of this amazing connection between all the values of the arithmetic-geometric mean when you do complex numbers. So that's pretty astonishing, because I started off with this really simple definition that these two sequences built from arithmetic means and geometric means, and here we are talking about modular functions and modular forms, and using them to prove a really cool theorem. So what does it have to do with Gauss? So Gauss basically lived from 1777 to 1855. His first published work was Discusiones, which is astonishing. It was somehow simultaneously his senior thesis and his PhD thesis. And he was basically one of the greatest mathematicians. But it turns out that a lot of stuff he did was never published. So after his death in 1855, people found an amazing amount of unpublished material, and it took them basically 60 years to actually get it all sorted out, published, and stuff like that. And so basically, it's unpublished material. It's called Nachlass in the German. So what did Gauss know about the AGM? I mean, some of my comments make it clear he knew some of this stuff. So for example, he basically knew everything in the previous part of the talk. Wow, that is mind-blowing. And he did this work between 1799 and 1800. He did all of it. So in one sense, modular forms have been around for a long time. Now it turned out, how much did he publish? Well, it turned out that he was doing a paper in 1818 on some astronomical calculations, and in that paper, this integral cropped up. So it turns out that he wanted to come up with a quick way to compute the integral. And of course, the point is that this converges. This is really fast to compute because that exponential convergence. And so we actually proved this theorem in the paper. That's where he did that change of variables that I wrote down. And that's where he made the quote. He wrote down, the formula said after the development is made correctly, it will be seen that. And also, just for connections with other parts of what you're studying this summer, I should mention that, of course, there's some elliptic curves lurking here. And that change of variables is actually a degree 2 isogeny from one elliptic curve to another. And so, again, there's a lot of stuff sort of hidden in the background that's going on. But it turns out that the rest of his work on the AGM was never published. So people started discovering it for the very first time in 1855. And so what I'm going to do is I'm not going to tell you the full extent of what he did. I'm just going to give you sort of a couple of snapshots to sort of give you a sense of sort of what Gauss actually did. And some of it's recorded in his mathematical diary. So this is something that he started in 1796. Basically March 30th. And this is the very first entry in the diary. And so he was 1 month shy of turning 19. And it turns out that this is, so Principium principles, so that's sectio, circulae, so that's, circular sections. So what do you think that letter is? It's an S. But what does it look like? It's an integral sign. That's because in the 18th century, sometimes, you see, here's an S that's written like a normal S, but for reasons that I don't understand, sometimes they wrote an S in this really elongated way, and that's why we use the integral sign. It really comes from exactly this kind of way people wrote S's, because the integral is supposed to be the limit of the Riemann sum, and so trying to capture that sum idea in the notation is where we get the integral sign. So anyway, so here's circular sections, and that's divisible. And that's geometrically, so he's doing geometric divisions. Now, here's another one of our S's. So here's my question. It depends if you've been watching Game of Thrones. So what's sept? 7. And that's decim. And so what's sept and decim? 17. So this is basically where he's saying I can divide a circle into 17 equal pieces by ruler and compass, so he's constructing a regular 17 God by ruler and compass, which is, the first genuinely new geometric construction in 2,000 years. So, this is big. And so there's, so it's, like I say, that's 146 entries. So there's the first one. He stopped doing it around 1814. And like I say, here's, written out, in a slightly more legible form is the very first entry. And it turns out that of these 146 entries, 10 of them deal with the AGM. So this is something he clearly, he thought it was good enough to put in his mathematical diary. And so it turns out that I'm going to do entry 98, which is in May 1799, and entry 109, which is about a year later. And so where do we get here? So here's, he wrote it in Latin. And so we've established that the arithmetic geometric mean between 1 and the square root of 2 is pi over pi tilde to the 11th decimal place. The demonstration of this fact will surely open a new field of analysis. So, so there's that arithmetic geometric mean that I showed you, in one of the first slides. There's that, number that, comes up. And what Gauss did is he noticed that these two numbers were equal to 11 decimal places, which means that Gauss knew this number. Many of you recognize the square root of 2. The question is, in the 18th century, there were mathematicians that actually were quite familiar with that number. And part of it is some work going to Euler. Because like I said, so there's our very first elliptic integrals. A lot of people played with it. This is sort of a variant of that elliptic integral. It's an extra z squared there. And like in 1786, basically Euler proved that the product of these two integrals is pi over 4. And he also given a numerical approximation for this integral. And yet, remember this integral right here is, pi tilde over 2. So that's this first integral. So the first integral is pi tilde over 2. This integral right here is that guy. That's equal to pi over 2. And so you do a little bit of math, you get that pi over pi tilde is that number right there. So that number was out there in the literature. And it turned out that we actually, these days when you check out a book from the library, nobody knows that you checked it out. But, back in the day when Gauss did, he would actually have an entry of, what journals Gauss checked out. And they can verify that he checked out the journal that had this paper of Euler. So it's so my guess is, Gauss had actually checked this out. He sort of had this number in his head. And so when Gauss computed this number, he said, hey, I know that number. And he said that, and so this thing, which is just, again, just, arithmetic means or geometric means, it's a really harmless kind of thing. To connect it to this kind of stuff, Gauss said, there's something here. And so that's what he said here, is that the demonstration of this fact will surely open a new field of analysis. And within a year, he actually found a proof. And he actually found several different proofs. But let me fast forward to a full year later. It says between two given numbers, there are always infinitely many means, both arithmetic geometric and harmonic geometric. Now this is something I haven't mentioned before, but the harmonic geometric mean is basically you sort of replace A and B with their reciprocals and sort of do the same kind of thing. But basically for the, so what he's saying is between any two given numbers, there's infinitely many arithmetic geometric means. So he's obviously now dealing with complex numbers. But it says the observation of whose mutual connection has been a source of happiness for us. Well, Gauss was sort of a little full of himself, but on the other hand, he was Gauss, so justified. So he really is talking about the counting many values that connect these guys, and the mutual connection, that's the theorem that we just finished proving, and here's his version of the proof. And it's not quite stated in total and complete generality. So it says the AGM changes when one chooses the negative value for one of, so it turns out that n prime, and double prime, and triple prime, those are basically en plus 1. So he sort of imagined making the right choice most of the time and just once making the wrong choice. And then it turns out that, so that's what I call U prime. So basically notice that, we have, the mu, the lambda, so it looks pretty similar. And you get the fact that there's only a 1 there instead of a d, and that's because you basically only made basically one choice, one bad choice at one point of the thing. And also it turns out that Gauss called that mu, he called that the Einfox to middle, which is the simplest mean. So that's why I call it the simplest value in my lectures, because that really is the terminology that Gauss used. So like I say, Gauss didn't have the full general theorem, but he clearly knew what was going on. Now, one of the things that we used in our proof of the main theorem was this fact about, when you take these, theta functions, their arithmetic-geometric mean is always equal to 1. And that was, when we did that and were sort of clever with it, we were able to actually get an approach to the whole thing. Well, it turns out Gauss knew this fact, and then here's how he states it. So this is in volume 3 of his collected works. So he calls it, so he says, so ergibt sich das höchstwichtige theorem. So that's most important theorem. And so, and it says the arithmetic-geometric mean between p of x squared and q of x squared is always equal to 1. So Gauss knew this result right here. So he really knew the theta functions. He knew how the identities work. He knew how this all related to the arithmetic-geometric mean. So all that he had nailed down really nice. Now also I talked about some fundamental domains, and I drew one picture of a fairly complicated one. Turns out that Gauss never really got around to writing up his stuff completely, so he never really did a complete treatment. So he had sort of bits and pieces here and there. But he did have some fundamental domains. He had the fundamental, because we talked about k prime of tau, that has a fairly complicated fundamental domain. But if you square it, it makes life a lot simpler. And it turns out that that's invariant of the group of gamma 2. Remember, that's the elements of SL2Z that are just congruent to the identity mod 2. And so he knew there was gamma 2 invariant, and he actually knew the fundamental domain. But it turns out what's interesting is that in publishing his collected works, they had to do it twice. And the reason is the following, is that here's what it showed in the first time. Now there's two things here, there's two aspects of this that are a little funky. So what's the first thing that's really strange? Yeah, so what is Gauss using? Is he using the upper half plane? He's using the right half plane. So that's a question. Suppose Gauss had published this stuff. Would you now then be studying the right half plane instead of the upper half plane? Now, what does that round for t and 1 over t mean? Well, it turns out that for the fundamental domain, what you want is you want the imaginary part of t to be between 1 and minus 1. That's what basically gives you these upper and lower things. And of course, that's not the whole story. But before I get to the whole story, I want you to tell me what's wrong about this picture. It's actually a bad drawing. What did they mess up? What are these supposed to be? They're supposed to be semicircles. They didn't know what a fundamental domain looked like in 1863. But Gauss knew in 1800. And so now it's possible that there were people studying stuff that actually did know what a fundamental domain was, but basically this particular editor, the people working with him, they were clueless. And so what should have been semicircles, they just put big parentheses because they didn't really understand the math that Gauss had done 60 years before. It took a long time for math to catch up to Gauss. And so they fixed it in 1900. This is 45 years after he's died. And now Felix Klein definitely knew what fundamental domains were. And so this is how the same picture appears. Now we really have the semicircles. And the point is that, what's the 1 over t? Well, the point is that you also want that to be true. And so like I say, so this inequality right here gives you the top and the bottom, and then this one right here says that you have to be outside of these two semicircles. And so Gauss really knew the description of that fundamental domain. So that's very definitely there. So now to finish up, I have two more slides. And so the first one is just to go back to his first entry, where he noticed this, and he said that understanding this will open an entirely new field of analysis. So the question is, was he right? Well, let's think it through. So it turns out that by December, so this is May, by December he approved it, and so we actually got a link between elliptic integrals and the AGM. And that's actually really nice, but I don't think that really constitutes something tremendously new. That's just basically a nice connection between two sort of existing mathematical objects. But then when you throw in the complex AGM and connection with modular functions, modular forms, then we really do have something genuinely new. And so in this case, Gauss really was true to his word. We really had something genuinely new that came out of this observation that these two numbers agreed to 11 decimal places. So the final thing is, some of what Gauss did actually had been discovered during his lifetime, and he commented on that. So here's a famous letter he wrote to Bessel in 1828. He says, I shall most likely not soon prepare my investigations on transcendental functions, which I have had for many years, since 1798, because I have many other matters which may be cleared up. And the answer is he did have many other matters, and also when Gauss wrote stuff, he wrote it in complete detail. And to do all this stuff that I've talked about in complete detail would be a huge project. So it just never got done. But it turns out that in the meantime, like in the, basically just a few years before the letter, sort of Abel had started doing his work on elliptic functions, and that was this wonderful idea about, instead of elliptic integrals, you look at the inverse functions, which are elliptic functions, and of course elliptic functions are then the things that parameterize the elliptic curves that you're studying. And so Abel and also Jacobi did a lot of really important stuff on this. And so Gauss says, Herr Abel has now, I see, anticipated me and relieved me of the burden with regard to 1/3 of these matters, particularly since he carried out all developments with great precision and elegance. Now, that looks pretty arrogant. Abel does this fantastic stuff. And it says, that's only 1/3 of what I've done. So the question is, and I should say that Gauss did have a complete theory of elliptic functions. That's something I didn't touch on in the lecture, but he did, take the elliptic integral, take its inverse function, and he had a nice, beautiful theory of elliptic functions. And so, when Gauss says that Abel is relieved of the burden with regard to 1/3, that is really true. But what are the other 2/3? Well, the answer is we've seen hints of that. So, of course, part of it is, one of the thirds is his work on modular functions and modular forms, stuff in fundamental domains and all that stuff. Because that stuff really wasn't at all anywhere in 1828. And of course, the Arithmetic-Geometric means is the other third. So again, even though it looks arrogant, he's actually telling the truth. So anyway, that's the end of my lecture. I hope you enjoyed it. I hope I surprised you a bit and showed you some really fun stuff. Thank you.
Questions?
How do we see that the infinitely bad choice is even clear?
So what happens is that every time you make a bad choice, then that has an effect several iterations later of making things drop in absolute value by half. So I think you improve a series of inequalities that show that if I make a bad choice at stage n, and by stage n plus 2, everything has gotten less than half an absolute value. So we do that infinitely many times, we go to 0.
Other question? I have a question. You mentioned that Gauss mentioned the product of the mean and the integral.
Yeah. Yeah. There was something on secular perturbations. But it turns out that there's lots of mathematical physics where elliptic integrals crop up. So what happened is in the process of doing some sort of asymptotic expansion, part of it involved an elliptic integral. And he said, oh, I know how to compute this. And they basically did that little bit of his theory there.
Yes, Keith.
So the breakthrough is noticing the numerical coincidence of m of 1 and the square root of 2.
Right.
Why was he looking at that choice of pair of numbers?
And I remember one time Percy Diaconis asked me that question, and I don't know the answer. And it's possible it was just coincidence. He possibly wanted to do something different. Turns out that there's certain, if you read some of the bits of history about when people look at, some of the very early work on elliptic functions, the square root of 2 crops up in various places. And so it's possibly said, maybe that's interesting. But the answer is, that's one of the challenges, and there's certain things in the history of math that if you look at the stuff, you can sort of see what happened, but there's certain parts of the motivation you're clueless. But at least, if you think about modern times versus now, Gauss left pieces of paper that we can look at. And these days, what are mathematicians going to leave by? And the answer is computer files that nobody can read because those computers will be totally out of date. So historians of math in the future are going to have a tough time with this period.
Are you getting spectated again?